So now I want to prove the theorem by Levitsky, which states that if R is a prime and PI ring, okay, I write PI algebra in order to have no problems with the definition of polynomial identities, then R contains no new ideals. Of course, different from zero. No non-zero new ideals. So new ideal. This simply means that this is an ideal of R such that for each I in I there exists some n such that I in power n equals 0. So every element is new, maybe of different degree. And if you consider arbitrary prime rings, it may happen that such a ring has new ideals. Although I don't know examples, and the theorem of Levitsky states that it cannot happen. It was proved 1950. So the proof goes in the following way. We assume that R satisfies a polynomial identity which is of some degree n. This is not this, and this is another n. So R satisfies a multilinear polynomial identity of degree n. And of course you can write this multilinear polynomial identity in the following form up to change of the variables. So this is f of x1 xn. It has x1 xn plus some a sigma x sigma 1 x sigma n, where a sigma is an element from the symmetric group which is different from the identity, and these elements a sigma are from the field. In the general case there should be some integers if you work over Z. And now we have, of course, if you have an identity simply of this form, you can rearrange the variables to have x1, x2, xn to be with a non-zero coefficient, so you can get such an identity. And now we have induction on n, on the degree of the identity. For n equals 1, there is nothing to prove. The identity f is f x1, this is x1 equals 0. So this means that R is the zero ring and nothing to prove. So we assume that this is true for if the identity is less than n, and we want to prove this for n. So we choose R to be prime. We assume that n is a near ideal which is different from 0, and we choose an element from a in some power k equals 0, and choosing, if k is minimal with this property, we choose b to be a in power k minus 1. This is still not 0. And b squared, of course, this is a in twice k minus 2, this is 0. Here we have that, since here k is bigger or equal to 2, of course. So we know that we have an element which is non-zero, and the square is 0. So there exists an element A in N such that the element is different from 0, but its square equals 0. So I call this element A, not B as what's here. So there is an element which with square equal to 0. And now we consider L to be the left ideal generated by A. So okay, this is my statement is not correct if the algebra has no 1, because this is the ideal obtained by multiplying by all elements. So A maybe is not here, but I consider this ideal. So this is the left ideal of R. And of course, L is still new because it contains the element so now I consider the following. So this is the left ideal of R. Maybe I should clean the other part of the blackboard. So I consider R1 to be L modulo R L intersect with L. So this is the right annihilator of L in R. So you know that by the lemma R1, which we proved, R1 is prime, a prime ring. And I want to show that R1 satisfies a polynomial identity of degree n-1. So how we prove this? We write the polynomial identity f which we have in the following form. We write first x1. So from all the places here we collect x1, and we have something g which depends on the other variables, plus some h depending on x1, xn, but here we have collected all monomials, all summands of f which start with x1. And in the other place you have all x1 is never in the first position. So now we take some elements R1, Rn from R. So we take any elements from R, and we do the following. We replace f, the elements, with the following. We have in the first place A R1, then we have R2A, Rna. So in the first place we have A R1, and the other places R is in the second position. Of course this is 0 because f is a polynomial identity of R, and these are any elements of R. There are some elements of R. But what happens? Here we have AR1, G, we have R2A, Rna, plus H, and here we have AR1, R2A, Rna. And now you see, in this place, this is 0. This is 0. Because R1, AR1 is not in the first position. So we have something. We have AR1 and maybe something here. Because H was the sum which didn't start with. And here we have obligatory something which is Ri with A. So you get here A0, A square which is 0. So the result is that we get that this expression, this is AR1 G R2A Rna. And this is 0. We repeat this argument with instead of working with this element, so we have now F, we take A, R2A, Rna. This is also 0, and by similar arguments, we get that A times G R2A Rna equals 0. So what this means? This means that if we take so we have that if you consider the two-sided ideal, so if A is the two-sided ideal of R generated by A, and B, this is the two-sided ideal generated by this element G. Here we get R2A Rna. So we have that AB equals 0. Why AB is equal to 0? Because the product of these two ideals contains either AG or contains I. So because AB is generated by AG and ARG. And in both the cases this is 0. So you have that this is 0. And now we have a two-sided ideal of R, and R of course is a prime ring. So this means that